Hi, I'm Antonio Sala, and in this video we are continuing our discussion of an example of a stochastic process, a Gaussian process, with two outputs. And in this video we will discuss the principal components, or in continuous samples, Karhunen-Loeve eigenfunctions. We had a stochastic process with two outputs, and we had some correlation between them, so that we got these sample realizations in which, functions go up and down somehow closely, and we explain that behavior with a component-based description, y equals cu, in which these components were independent, cross covariances were 0, so covariance between the two outputs could be expressed with this matrix, and this ended up being a 2x2 matrix with some covariance structure, yielding these representations. These were, let's say, realizations of the components that, when added together, resulted in this kind of realizations. The common component is in dashed yellow. What we are going to analyze now is the principal components, in the sense that, in these test samples, we duplicated them, first half with label 1, second half with label 2, this kind of stacking my samples. So I had 161 samples, and then two labels, then I got a covariance matrix of 322 random variables that I would sample. But now, principal component analysis amounts to analyzing the eigenvector eigenvalue structure of this super big covariance matrix. So let's do it. If I compute eigenvalues and eigenvectors, in D we have the eigenvalues, and as they have units of variance, let's say, its square root has units of standard deviation. I add this thing just for numerical issues to avoid negative eigenvalues due to tolerance stuff. But then, if I print these eigenvalues square root, then I get that the variability, standard deviation, can be expressed as the sum of some components with these standard deviations. And as you see, kind of the first 6 or 7 are responsible of most of the variability, and then we have a bunch of other ones, and instead of 322, most of the variability can be explained with 20, 30 or something like that. Variance is the square of this. So what is the meaning of these components? Well, if I plot the eigenvector times the component amplitude, then we will be able to understand the meaning. I will start with the first component, and then, as I was stacking my samples in the covariance matrix as this, then the first half correspond to things associated to label 1, the first function, second half was associated to the second function. So if I plot the first half of the eigenvector and the second half of the eigenvector, I have this first principal component. As we see, it has large amplitude. We'll compare with other ones in a minute. And it's somehow the fundamental harmonic, and as the common component in F1 and F2 had a large variance, then this large variability is explained by a common component. As red and blue functions are almost copy one another in phase and same amplitude. If we now see component 2 superimposed to component 1, then it has also a large amplitude, just a little bit less, but 2.40 something, 2.1, and somehow it has double the frequency, sort of. If I now plot the third one, here we have it, a higher frequency harmonic, let's say, but still red and blue are practically copies one another, so it's the variability due to the common component. And I can go on component 4, component 5, component 6, they are in increasing frequency, decreasing amplitude, but mostly blue and red are copies of one another, more or less. And in this component 7, red and blue start to depart, but they are still in phase. And component 8 is now mostly associated to the first function, f1. The red one has low amplitude. And component 9 is the first one that tries to explain the differences between f1 and f2, because the components are, in opposite phase, let's say. So this one starts explaining the difference between the functions, but okay, it has much lower amplitude than the previous components that explain why both of them are equal, up to 6, 7. Component 9 here, we are now entering this region in which we are starting to explain why they are different. The other components, mostly except component 8, maybe explained why they were equal, and as the functions were very similar, most of the variability was explained by these equal components. So this was component 9, and then we have a bunch of harmonics. Component 10 explains the difference at double the frequency. Component 11 has triple the frequency. Component 12 quadruple the frequency. And now we have component 13 that again is associated mostly to f1. And well, we can go on drawing more and more components. This one is also associated, let's say, to large frequency variations of f1. And well, we could be analyzing each one of them, but well, component 25, again, high frequency stuff on f1. This is component 28, which has low amplitude, but it's associated to only f2, high amplitude in the red line here. So we have, components. Some of the components are associated to both the function equal, some others to both of the functions opposite phase, some others to only the blue one, some others to only the red one, f2, and well, so on. So you can download the code again and play with whatever components you wish, but okay, once we reach high numbers, component 38 is again high frequency wiggle of the second function, and higher components still wiggling the second function, and somehow the amplitude, if we increase, this is 58, decreases up to negligible levels, and overall most of the variability is given by the first 10 components, let's say. Explaining with another components, not these ones, the variability of this kind of realizations of the function. So well, as I said, you can download the code with the link in the description. So we finish here. In this video, we have discussed the principal component analysis of this stochastic process, in which we had 3 components, independent ones, but not principal components. And the principal components were a sort of waveforms, in which, well, some of them were copies of one another in f1 and f2 due to the common component, and some others explained the wiggling at higher frequencies of f1, f2, or the difference between f1, f2, etc. So this is it. We finish now. Thanks for watching.